Okay, hey class. So first things first, we're talking about in chapter 5 is we're talking about when we have an inclined plane, right? We have our angle here theta, and we have a box going ahead, and it's going to sit on this inclined plane. And we're talking about when this is going to be in equilibrium. So we're going to have a rope here with a tension T in it. And what we're gonna do is we have a force here, and we're gonna call this our weight. So this is just from last chapter. W is equal to mg, where g is equal to negative 9.81 meters per second squared, and mass is some undefined quantity that we're going to we'll define in examples later. So what we can do is we want to show that this is in equilibrium. The free body diagram for this we'll draw in just a second, but first we have to break down W since it's on an incline. So you're going to have a force this way, a force this way, and so all we have to do is we break this down into a regular triangle. So we can move this force here, and then this one is going to be W, like we see here. So now this is going to be the same as a triangle here, and that's going to be the same angle theta as it here, because these are going to be similar triangles. And so we can start breaking this down. This is going to be our A, this is going to be our O. So then we can use our trigonomic functions. And I'm writing them up here at the top. So first thing we can do is we can break this down, and we can say that we have cosine theta for our adjacent is going to be A over H. So now in this case, H is going to be W. And then solving for A, we get A is equal to H, or I can replace that as W now, cosine theta. And we can do the same for the other trigonomic function, where O is equal to W sine theta. So the force that points here, this is going to be our O, and there's our A. And so then opposite to our A, we're going to have our normal force M, which again is just the negative of A. So then we have that N is equal to negative W cosine theta. And then the force that pulls this down, or is going to be the opposite tension, so then T is going to be equal to negative W sine theta. Because T has to be at least strong enough in order to, or the rope has to be at least strong enough to hold this block in place. So now what we can do is we can draw our free body diagram. So we have our mass here, and we're treating it like a point mass. And then in this direction we have N. In this direction we have T. In this direction we have W sine theta. And then in this direction we have W cosine theta. And then down is W. And we've broken down W into its components here based on the angle of the inclined plane. So now, in this case, we can say that all forces here are going to be equal to 0. So then we can say f of x, or the sum of f of x, is going to be equal to 0. So in order to satisfy this, we just have, in this case, t plus o in this case, where o is the opposite here. And so then this is just going to be equal to negative w sine theta plus w sine theta. And we see that this is true. And then same thing for the y components, even though this is trivial, because it's just the normal force and A. So then this is going to be equal to 0, or this is equal to n plus A. And so then that's just going to be equal to w cosine theta. And technically, since we're using this as the normal force, this is going to be negative plus w cosine theta. And we see that this is equal to 0 as well. So now we've talked about it in equilibrium. So now let's say we snip the rope. So when we snip the rope, now O is only force in the x direction here. So we get rid of this guy here. But now we have to apply the frictional force. So in this case, the new force that points in the y direction here for static friction is going to be Fs is going to be this here. Now we can if we assume, I'm trying to get this so this is focus this. I'm gonna make this a little bigger. Yeah, there you go. Now you can see it. And so let's assume that here we have that Fs is less than O. So then we can use the force of kinetic friction. Okay, so back to what we were saying, we're going to assume that this block is going to break static friction, and then F of k here is going to be mu of k n. And so now we can adjust f of x to be equal to negative mu of kn, where n is just equal to w cosine theta. I've written the negative a little early. It should have just be mu of kn, and then you'll add on the negative after you plug in n. So now we have these two forces together, and depending on the angle, we can see how quickly this block will move down this ramp, or what the acceleration will be. Because what we can do now is, so since this is no longer equal to 0, or at least this should still be equal to 0, because it's not going into the ramp, it's not flying off the ramp. So it has to be, this still has to be 0, and this is still true. But now we have this, and this is going to be equal to ma, like we had before. And so then when we add these up, we can solve for the acceleration of the block on the ramp, and now we can say that A is going to be equal to mu of k w cosine theta plus, or negative, mu of k w cosine theta plus w sine theta all over m, which now we can decompose w into m and g. And then there you have it. You can also factor out a g here and take the m out as well. And so then this will now look like a is equal to negative, actually we gotta take this out. That's what I just said. Okay, g over m oh, the m cancels. What am I saying? Yeah. So then we can say that g sine theta minus mu of k cosine theta. I'll write this a little bigger. There we go. And so now this is our expression for a, which we see our units check out because sine of theta is unitless. Mu of k is a ratio between fk and n, and cosine theta is also unitless. So the only thing that has units in this equation is g. Okay, so next up, class, we're going to be talking about forces in circular motion. So now, circular motion is basically the same here, and we'll talk about it a little bit more as we go on to rotational dynamics and rotational kinematics. But we have, remember that we have a radial that still points inwards, and so if a radial points inwards, then the sum of all forces here also points inwards. And so we have, say, velocity in this direction here, v, and this is a vector, this is a vector, this is also a vector. So let's keep our hats straight. And so what we can end up saying is that from before we know that A is equal to Vt over R. Well, Ma then, or the force here, is just going to be equal to mv squared over R. And so then the period of this motion then is just going to be, or we can also describe this in terms of the period, for 4 pi squared R over t squared. And so what we've done is we've inserted the circumference into this, because remember we talked about how the circumference of a circle is equal to 2 pi r. So this is c. And so then this squared is going to be equal to 4 pi squared over r squared. And so that's, you see, that's where there's an r on the bottom, so one of the r's cancels out. And so this is how we describe this as the period, or within the period of the motion, for the time it takes for this to take one loop around. One more thing that I'd like to point out before we move on from the circular motion example is that when we have the circumference, right, this is basically our distance. So if we're using just our distance formula, with v, and we're just going to say that v is just our speed, and we have d is equal to vt, right? So if we solve this equation for v, we'll have d over t, where in this case we're going to change t from lowercase to uppercase because it's the period here, or the time it takes for this this object to complete one rotation here. And then if we square this, we get that this side is also squared, and that's where this c squared comes from, right? Because c is the distance that this object travels, and so we can plug in c for d, and that's where we're using our square from, and that's where this extra factor of t squared comes from. And so then we plug that in here, and this is what we yield from that substitution. So let's do this a little more explicitly. So v squared is then equal to 4 pi squared r squared over t squared. And so then you can see how the r's will cancel once we plug in v squared. I'll do that explicitly. So I'm actually adding in the m here now, even though it should have been there in the first place. All you have to do to convert the acceleration to a force here is to add the m. And so then we see that one of the r's cancels when we plug in this. So we have r here. And so that eliminates the denominator, and then we just have to tack on r period squared. And then so this is the force due to the radial acceleration. Okay, so next up, class, we're going to do a couple examples. So in this first example in the book, we have a ceiling here, and we have a rope attached to the ceiling here, and we have a person holding on to it. And so first thing we got to do is draw a free body diagram for this. So we can do that. So we know that the person has a mass m, and that w points downward like so. And so we know that if we take this as a point and we say that this is w here, then the tension in the rope has to be equal to this, as we're going to call this TR on G. And then this is for the gymnast. And so what we can do is we can say that we can draw it from the rope's perspective. And so what we can do is we can take some random point on the rope, and we can say, all right, well, this is now the tension of the rope on the ceiling, or the ceiling on the rope. And this one here is going to be T gymnast on rope. So this one is taking a rope-centric point of view, and this is taking a gymnast-centric point of view. So and rope. So first things first, we can evaluate the weight of the gymnast, and the weight is just going to be W is equal to mg. And all we have to do is multiply the mass by gravity, which in this case is going to be 9.81 times, or meters per second squared. And so now the next thing we have to find is what is the force, magnitude, and direction does the rope exert on her. And so we can use Newton's first law. And so since the gymnast isn't falling, we know that the tension, or TR on G, is just going to be the negative of her weight. or his weight. So sigma Fy is going to be equal to 0, and so that's going to be equal to mg or W minus TR, and I'm just going to abbreviate this as TRG, T rope on gymnast. And so then we can solve this equation here, and we can say that W is equal to TRG, but we also have to account for this is just going to be the magnitude then. We know that this is pointing in the opposite direction, but the magnitude here is going to be equal to mg. But we know that these guys are going to be opposite of each other here, because they have to equal, because this is supposed to be a plus, and then and this is just the quantity of this. So we know that W is going to be equal to negative T RG. Okay. And then next up, we have to find what the tension on the top of the rope is. And so we basically do the same process here. We say that sigma Fy is equal to 0. And we have this here, this connection here, because we know by Newton's third law that if we are going to reverse this, so we know that TRG is going to be equal to the negative of TGR. And then since we know that these are also going to be the negatives of each other, you can just solve this using Newton's third law, and you can say that TCR is going to be equal to TRG, and so then this is going to also be mg. This would be G of R. I got them mixed up. Okay, class, so continuing on, one big topic that we have to cover here is going to be equilibrium. So we're going to talk about tension, and so we're going to have this O-ring here, right? And so there's going to be a ceiling here and a wall here. And now the purpose of this is that we are lifting an engine out of a car. And so the engine is going to have some mass M, and we know that W is pointing downwards, and that from our last example, this is T1, we'll denote this as T2, and we'll denote this as T3. So now in this case, we know that W is going to be equal to T1 because of what we did last time, and because of Newton's first law. So if we wanted to rigorously do this, we could write the sum of Fy is equal to 0, and so then these two have to add up to be 0, and so then in this case we'd have to go T1 plus negative W is equal to 0, and so then we get that these two are equal to each other. Excuse my phone. Okay, so next up, one thing that we have to do is that when we're splitting this into its components, this is going to be theta. This is going to be aligned with the negative axis. One thing that we can immediately know is that when we break this down into components here, there's going to be a component here. This is going to be T3y. and T3x. Now, if the engine's at a standstill here, we know a couple things. We know that if we do the sum of our forces in the x direction, then this is going to have to give us T2 T2 plus T3x is equal to 0. And so then, if we take one or the other to be positive, then if we take this axis to be the positive axis going this way, then T2 has to be negative. So then T2 is equal to T3x. And so another thing that we can do is we can say, okay, well, what's the sum of all forces in the y direction? And so then we can say, all right, well, T2 doesn't contribute anything to the y direction because all of it's in the x direction here. So we're not going to see a T2 show up in this Fy, or the sum of forces in Fy. So next thing that we'll do is we can say that if we're taking the positive direction to be up, we can say that T3y minus T1, well, it should be plus negative T1 is equal to 0. But we already know what T1 is. T1 is just equal to W. So then this is going to be equal to T3y plus negative W equals 0. So then T3y is equal to W. And so now what we can do is we can use our trigonomic identities to break this down just a little further. We don't need the TOA, but we'll make sure that we get into what we really need. So again, we see that this is going to be our adjacent, this is going to be our opposite, and so then T3y is going to be equal to T3 sine theta. And then over here, Tx is going to be equal to T3 cosine theta. And so we've here now solved this algebraically. And at this point, all we need to do is we just need to solve. If we're given the angle and we're given the mass of the engine, we can solve for T3 here. So then T3 is equal to W over sine theta. And here we know what T3 is, and so we can plug T3 in here. And so then T2 is equal to T3, which is, we know, is W over sine theta cosine theta. And so this can be rewritten as cotangent. And now we have an expression for T2 and T3. And we already know what T1 is. And there you have it. We have now solved for all three tensions. Where is it? There it is. And we have effectively solved this problem. Okay, so next up, class, I really wanted to talk about friction. And so we have an example here where we have a box, right? And we attach a little ring to it and a rope. And so box has mass M, and we apply some force here and we pull it with some tension. So we know a couple things, W, N, and we know our friction equations. We know that Fs is equal to mu s N, and Fk is equal to mu k n. So right now what we can see is that mu of k here is going to be a ratio of fk and n. And so this is f due to friction here. And so what we can do is, as we increase, I'm going to draw here a graph. And so this is going to be f in magnitude. This is just going to be a friction here. And then what's going to end up happening, not the right color. Here we go. We're going to have this is going to be the force of static friction. And then once this is broken, we can draw an asymptote here. And this here is going to be Fs max. And then once this is broken here, this is going to drop down to approximately what Fk is. So this is going to peter out like this. And so it's going to bounce up and down here, right? But this line is essentially constant, even though it's moving up and down. But if you take the average over all of this, this is the constant line that you get, and this is going to be equal to F. This is going to be Fk, or the force due to friction. And so now we can see that this is some cutoff point here, where eventually T becomes greater than. This is the point where T becomes greater than Fs max. And then this is what the force due to kinetic friction will look like after this condition is broken. So if we apply any force T that is less than Fs max, the box will not move. So then when we break this, we can say that Fx is equal to ma, and furthermore we can say that Fx, or the sum of all F forces, is going to be T plus Fk. And so what's end up happening is we're going to have Fk is going to point in the opposite direction. And so then we can start plugging in what Fk actually is. So in this case, Fk is equal to mu of k of n, where this is equal to mu of k mg. Now, no, that's probably a little difficult to see, but this is mu of k fg, or mg. And so then we can plug that in here, and so then we'll have that T plus mu of k mg is equal to ma. And so then we can say that A is going to be equal to T plus mu of k. And then I'm going to simplify this. And so this is going to be T over m, and this is going to be mu of kg. So what we've done is we've divided m from both sides. So then you have T over m here, and then mu of kg over here. And so just remember that this g here is negative. So then what's going to end up happening is that this portion here is overall going to be negative, and this portion here is overall going to be positive. And so and one thing that we know is that T was greater than Fs max, and Fs max was going to be greater than F of k. So we know this magnitude of t over m is going to be greater than mu of k g, and so we know that this overall answer is going to be positive. And so this box will move in the direction of t. I've done this here just to make sure that everybody's aware that the frictional force is always going to point opposite to the force applied here. So in this case, it's going to point opposite of t. If you're pushing it from the other side, that frictional force is still going to apply in the opposite direction. So whatever way that the object is moving, friction is going to oppose that motion. Okay, class, so the last thing that I do want to cover before we move on for today, we move on to bigger things, is I want to cover drag force specifically. So when you have an object falling, there are two different types of drag forces. There's the one where F is just going to be equal to is going to be a function of V. And so if you were to take and you were to increase your velocity, you're going to have this linear increase at a constant k, and so F is going to be then equal to kV. This is going to be at low speeds, and then eventually you're going to have a term that's going to be proportional to the velocity squared. And so if we were to plot that on a graph like this, it would look like this as a quadratic. But if we were to plot it versus velocity squared, it would be a constant value, and this constant value is going to be d, and this is going to be just resistance at a high speed. And so then this equation is going to be F is equal to dV squared. Now, so then you have to account for, so this is high speed and this is low speed here. And so if we have an object that is falling through the air from a very high height, we're going to have that at this point, we're going to have sigma Fy is going to be equal to mg and then plus negative kvy. So we're just taking the y direction. And so then all of this is going to equal ma. And so at this point, we can say that A is going to be equal to mg minus kvy over m. We can say that A is equal to g minus km over y. And so we can see that g right here is our gravity, and then we're going to have an extra term here that is going to cancel out some of the magnitude of gravity, and so it's going to make the acceleration less than gravity. And so as v increases, this term gets bigger and bigger, and if we solve for the point where the acceleration is equal to 0, so we set this whole thing equal to 0, we can then get, I'm going to read some of this real quick, just so we have a clean derivation here. So then we're going to have a point where these two are equal to 0, and so we can say that then that g is going to be equal to km vy, just by adding km vy, or k over m vy to each side, and then we solve for vy, and then we finally get that we have mg over k, and then this is going to be what our terminal velocity is going to be. And k is going to have the units to cancel out whatever it needs to in order to get the units of velocity here. And so a couple things that we can do here, we can do another couple things in order to find the position here. So what we're going to do is we're going to use our expression over here that we obtained. Again, mg minus kvy. So then we're going to have ma is going to equal mg minus kvy. And then we can say that that this is going to be dv dt, and this is going to equal mg still. And from here, what we can do a couple things. We can perform something called separation of variables, and what we're going to do here is we're going to get all of the v terms to one side and then move the t over to the other side. So you're going to have dt over here, and we're going to have k and vy over here. So then what we can do is we can rewrite this as negative km, because we can divide out m here. And we can say that we can integrate from 0 to v, and then this is going to be dvy over vy minus vt. And so what we've done here is we have what this is going to be our terminal velocity, right? So we can rename that vt. And so we were going to replace mg over k, because we can divide this entire equation by k. And so then this here is going to be, so if we divide this, we can say that this is mgk, and so then this is vt here. And then if we divide it, this is going to be canceled out. And then if we divide both sides by m, we're going to get over m, right? And so then we can say that this is true. And we have to integrate on this side as well. So now, moving forward, we can just integrate this, and this side is going to be the ln of vt minus vy over vt. And this is going to equal negative kt over m. And so then we can take the e of both sides. So then we have vt minus vy over vt is going to be equal to e to the ktm. And then we can rewrite this as 1 minus vy over vt equals e over m over here. And then we can multiply, we can subtract 1 to each side, take the negative of each side, so that we get vy alone. So then vy is going to be equal to, I'll start performing these steps here. So then we can have, we're going to have e to the negative kt over m, subtract 1, gets rid of that, and then take the negative of both sides, and then this is going to be equal to vt 1 minus e to the negative kt over m, and there's what vy is. And so So then what we can do here is we can also just take the derivative here and get back what AY is. So taking the derivative here is going to yield, so let's just do this real quick. So we're taking this with respect to t, so I guess I should put this as a lowercase t. Sorry, I'm used to statistical mechanics at the moment, where t is a capital T. Okay, so this is going to be a time derivative here. And so we can again plug back in what Vt is. So then we're going to get that Ay is going to be d dt of mg over k minus mg over k e to the negative kt over m. Okay, so when we take the time derivative of this is going to be equal to 0 because it's just a constant. And then when we take the time derivative here, we're just going to get the factors of e, the factors not including t are just going to come down and be multiplied by this. And so then we get that Ay is equal to mg over k, or negative, and then we have to multiply it by negative k over m times e to the negative kt over m. So then k cancels here, m cancels here, the negatives cancel, and then so then Ay is going to be equal to g e to the kt over m. Again, this is g, and I'll write this in an easier to see form. We're going to use exp as an exponential, and then we can say negative kt over m. And so now we've solved for what our acceleration Ay is. And in addition, we can also take a second derivative of Vy, or we can integrate again by getting all of this on one side, and we can reintegrate and get the position as a function of y. So why don't we do that actually? So then we have here is we have Vy is just going to be dy dt here, and this is going to equal Vt 1 minus e to the negative kt over m. And I'm going to plug back in again what Vt is, and I believe that was just mg over k. So I'm going to plug all of that back in. And so then in this case, we don't have any y's in these terms here, but we do have a t over here. So we can just integrate dy from 0 to y, and we can integrate this side mg over k, and we can do this term by term from 0 to t minus mgk, and this is dt, e to the negative kt over m dt. All of this is just a constant with respect to y, so we get mgt over k, and we get mgk, and this is also going to be from 0 to t. And here, in here, this integral here is just going to be e, I switched colors by accident, is going to be e to the negative km t all over a, which is going to be, in this case, is going to be k over m. So then we get a k down here and an m here. So we just had to flip the constants here. And since it's an integral, you have to divide by it. So we have vt t minus vt m over k e to the negative kt over m. And so this should be correct. Okay, so I see what I missed. When you're integrating from 0 to t, when you plug in a 0 here, you have to subtract a 1 here, and this was positive, or this was already negative here. So then when we factor everything out, we'll get that y is going to be equal to vt, and this is going to be a minus 1 minus e to the kt over m. And this is negative again. And we can factor out, or we have these constants in front too. So this is just going to be, we still have our constants here. This is going to be m over k. And this should also be an m over k. So we can factor that out. And so then this should be, and then there's also a t here. So this should be vt t minus mk 1 minus e over kt m. And there's a factor of vt in front of everything, because we have that here. So we can factor the vt out of everything. We have our t. We have our mk that gets multiplied by the multiplied by 1 when we put in the 0 here, and we have our factor, or we have our 1 that we plugged in t for. And so this will be your answer. Vt times the quantity t minus m over k times the quantity 1 minus e to the negative kt over m.